All right, today we're going to crack the code on something you probably thought you left behind in algebra class, the humble straight line. But we're going to transform it from just a problem in a textbook into a powerful tool you can actually use to predict things. Everything from energy trends to the cost of your next big project. So how can a line predict the future? I mean, it sounds like magic, right? But it's not about crystal balls. It's all about the simple, predictable nature of a line. And we're about to see just how that predictability lets us model the world and forecast change with some pretty incredible accuracy. So here's our game plan. First, we'll see why straight lines are so powerful in the first place. Then we'll dive into the classic blueprint, y equals mx plus b, and figure out how to use it. We'll even see what happens when lines interact with each other. And finally, we'll get our hands on a master tool for finding hidden patterns in messy real-world data. Let's do it. Okay, first up, the power of linear patterns. And honestly, once you know what you're looking for, you start seeing these things absolutely everywhere. I'm talking about your phone bill, the way a plant grows taller. It's all around us. Just think about it for a sec. A recording studio that charges a flat fee just to walk in, plus an hourly rate? Yep, that's a straight line. The steady growth of renewable energy, year after year, you can model that with a straight line too. These are real situations with clear, predictable patterns we can describe with some surprisingly simple math. So, how do we actually describe these patterns with math? Well, we're going to start with an absolute classic, the slope-intercept form. This is our fundamental blueprint, our go-to for building and understanding these linear relationships. You've probably seen it a million times. Y equals mx plus b. It's like the universal recipe for a straight line. All you need are two key ingredients, m and b, and you can create almost any line imaginable. But what the heck are m and b anyway? Let's break it down. M is the slope. Just think of it as the rate of change, the per anything cost, the per hour charge, the per mile fee. That's your m. And b? That's just the y-intercept, which is a fancy way of saying the starting point. It's that flat fee you pay before anything else happens. So really, it's all just about the rate and the start. That's it. So let's put this into practice with that renewable energy example. Back in 2007, that's our starting point, our B. The US generated 105 million megawatt hours. The rate of growth, our slope M, was a steady 22.8 million more each year. You just plug those two numbers into the formula and bam, you've got your model. Y equals 22.8x plus 105. Okay, so what's the big deal? Why bother with the model? Well, this is where the fun starts. We can make predictions. We can ask, hey, what about 10 years later in 2017? We just plug in 10 for x, run the numbers, and what do we get? The model predicts 333 million megawatt hours. That's the power of this simple blueprint. Now, slope-intercept form is awesome, but it does have one weakness. You have to know that starting point. But what if you don't? What if you don't have that specific piece of info? Well, for that, we need a more flexible approach that can work with any point on the line. I mean, think about it. What if you don't have that perfect data for year zero? What if all you have are a couple of snapshots from the middle of the trend? Are you just stuck? No way. Let's look at this order for foam hands. We can see that 4 hands cost $34 and 6 hands cost $46. We don't know the initial design fee, but if we look closely, the cost goes up by $12 for 2 extra hands. A little quick math, that means our rate of change, our slope, is $6 per hand. So we have the slope, but we still don't know that starting fee. And this is where our next tool comes in handy. It's called point-slope form. Think of it as the Swiss Army knife of linear equations. It lets us build the exact same line, but instead of needing that specific y-intercept, we can use any point on the line we want, as long as we know the slope. So we just take our slope of 6, grab one of the points we know, like 434, and plug everything in. After a little bit of algebra, we get our final equation, and what does it tell us? It reveals that the hidden initial design fee, our y-intercept, was $10 all along. We found the starting point without ever having it to begin with. Pretty cool, right? All right, so we're getting pretty good at building a single line. But what happens when we have two lines interacting in the same space? How do they relate to each other? Let's take a look. This is actually beautifully simple. For two lines to be parallel, like train tracks running alongside each other forever without crossing, They have to have the exact same slope, the same steepness. And for them to be perpendicular, intersecting in a perfect 90-degree angle, their slopes have to be what we call negative reciprocals. Now, negative reciprocal sounds super complicated, but it's not. All you do is you take the fraction, you flip it upside down, and you change the sign. So the negative reciprocal of 2/3 is -3/2. That's it. And this one simple rule is the key to creating that perfect 90-degree angle, which, believe it or not, has some seriously important applications. So why does this even matter? Well, picture this. A search and rescue helicopter is over the ocean. For the crew, the fastest, most direct way to get to a straight shoreline isn't just any path. It's the path that is perpendicular to it. So if the shoreline has a slope of, say, -2/3, the rescue crew knows they need to fly a path with a slope of +3/2. They plug that into their navigation and boom, it gives them this equation, the most direct and fastest route to the rescue. This is a perfect example of math in action, saving precious time when it matters most. Okay, we have built a really solid toolkit so far, but now we have to face our final challenge. The real world is messy, so we need one more master tool to help us find patterns even in imperfect data. Yeah, real-world data almost never falls on a perfect, clean line. It's usually scattered all over the place and can look a little chaotic. So how in the world do you find the hidden trend inside a cloud of points? We use something called a line of fit. Think of it as our best guess, an approximation that we draw to cut right through the center of that data cloud. It's really a way of finding the signal in the noise, capturing the general trend even when the individual points don't line up perfectly. Check out these weekly DVD sales. The numbers don't decrease by the exact same amount each week. It's a little jumpy, but if we plot them, you can clearly see a downward trend. By drawing a line of fit through the middle of these points, we can see that sales are decreasing by about $2 million each week. It gives us a simple, powerful model for a messy set of data. So, there you have it. We've gone from a simple formula to a powerful set of tools for modeling the world. Now that you know how to see the linear patterns all around you, the only question left is, what real-world trend are you going to model first?